Lecture 5b on weight and inertia. Inertia is a measure of how difficult it is to get an object to change its motion. For instance, you may have a friend you have difficulty getting off the couch. That would be inertia in the everyday usage. In Physics 222, when we learn about thermal physics, we'll talk about a thermal inertia, the difficulty of getting an object to change its temperature. Here, in Physics 220, inertia is a measure of how much force is needed to make an object accelerate. For instance, this elephant is a push is applied to the elephant. The elephant will accelerate. Notice the elephant's on roller skates from this push. If the same exact push was applied to a dog on roller skates, it would accelerate or change its motion a lot more because it has less inertia, less stuff, less mass. So what you push matters. Here's a graphical interpretation of inertia. On this graph, we see the vertical axis has acceleration. The horizontal axis is a measure of force, the amount of pulls of a rubber band from your textbook. Notice what's being graphed is you increase the amount of rubber bands, the amount of pulls, increase the amount of force, it results in more acceleration, and the relationship is linear. 2 rubber bands or twice the force gives you twice the acceleration. 4 rubber bands or 4 times the force gives you 4 times the acceleration, etc. What is this proportionality constant? How much force relates to a certain amount of acceleration? Well, the slope of this relationship is rise over run. The rise is acceleration, the run is force. So acceleration divided by force is equal to the slope. But we know what acceleration divided by force is. It's Newton's second law, 1 over the mass. We measure the amount of force and see the result, the effect of it being the acceleration. That's why it's plotted as force on the horizontal axis and acceleration, the result, on the vertical. So our slope is 1 over the mass. So if we increase the mass, we would have a shallow slope, a smaller ratio. If we decrease the mass, we'd have a steeper slope. Looking at this graph of acceleration versus force, we see we have 4 slopes. The steepest slope means we get a certain amount of acceleration for a particular amount of force. The shallow slope, the 4th slope, a quarter of the steepest slope, means for the same amount of force we get a quarter of the result, a quarter of the acceleration. Or I need 4 times the force to get the same acceleration that I would get on the steepest slope. Which slope relates to an object with greater mass? The shallow slope, the slope with a quarter the slope, has 4 times the mass. I get a fourth of the effect, a fourth of the acceleration, with more stuff, more mass, with more inertia. The greater mass, the greater inertia, the more force is needed to get the same acceleration, with the less acceleration you get with more inertia. This is a graphical form of Newton's second law. Recall that Newton's second law says that a mass resists acceleration. That's the idea of inertia. For a given force, the greater mass, the lesser acceleration. That's what we just saw graphically, and we just discussed in terms of pushing on the elephant or pushing on a dog. Acceleration is the result of adding up the forces. It's a result of the net force. Not just any old force, but it's the result of the net force per the amount of mass, which is a measure of the amount of stuff, inertia. So the sluggishness of objects is called inertia, the tendency of an object to resist a change in motion. Diagrammatically, we apply a force to, say, a mass, a block, you get an acceleration. If I apply that same force to 3 identical masses, 3 identical blocks, I get a third of the acceleration. Equivalently, if I apply the same force to something that's 3 times as massive, I get a third of the acceleration. How does mass differ from weight? Well, weight is a force. Weight is from the pull of the Earth, or pull of a planet, or pull of any matter on some other matter. The force of gravity gives things weight. If an object is in free fall, such as in this force diagram, the weight is down, and that's the only force vector. That's our net force. So the object must be in free fall. The Earth is applying this net force, pulling it down. The Earth is pulling it down with a net force equal to its weight. Its weight is the power, the force of the Earth. So the net force is mass times acceleration in the y or vertical direction, which we call mg. So the net force is mg, and that net force is the one and only force of gravity, the force of the Earth on the object, which is its weight. Therefore, weight is equal to mass times gravity when an object is in free fall. But it turns out that weight is equal to m times g, regardless if the object is in free fall, or at rest, or rolling, or sitting on something. For instance, the basketball here, if the one and only force in this basketball is the force of the Earth, the force of gravity pulling down on the basketball, then the weight is the net force. So the weight is equal to the mass times acceleration, or mass times g in free fall. But the Earth doesn't care whether the object is in free fall, whether the object has been tossed for projectile motion. The Earth still pulls down on it, still has the same weight, mass times g. The Earth doesn't care whether the ball's at rest or the ball's rolling along the floor or bouncing. It still pulls down with the same exact force, which is equal always to mass times gravity, or mg. So weight is the force of the Earth on the ball, equaling mg always, even if it's not in free fall, even if it's not accelerating, even if it's at rest. The value of the force on the Earth on the basketball, or the force on the Earth on any object, is m times g. Mass. If we put a 1 kilogram object on a scale that measures pounds on the surface of the Earth, it'll record 2.2 pounds is equivalent to 1 kilogram, or 1 kilogram weighs at the surface of the Earth 2.2 pounds. In an equation below, that mass, 1 kilogram, times it by g, is equal to 2.2 pounds. That's our force. But we represent the force in units called newtons. So 1 kilogram times g, if we represent g to be 10 meters per second squared, roughly, approximately, then 1 kilogram times 10 meters per second is equal to 10 newtons. And newton is our unit of force. So 1 kilogram, a mass of 1 kilogram, is a weight of 10 newtons. Mass is different than weight. Weight is a force. Mass is a measure of inertia, or the amount of matter or stuff, in a sense. Thus, 1 kilogram weighs 10 newtons on the surface of the Earth, where g is about 10 meters per second squared. And 2.2 pounds is approximately 10 newtons. Or 1 pound is very roughly 5 newtons at the surface of the Earth. So a mass of 1 kilogram has a weight of 10 newtons. That is a conversion that you should memorize. 1 kilogram is about 10 newtons, which is about 2.2 pounds. So 1 newton would be a tenth of a kilogram, or 100 grams. An apple, Newton's apple, an ordinary apple, is about 1 kilogram, or about 100 grams. So the weight of an ordinary apple is a newton. So things that weigh newtons are the weights of apples. Things that are heavier, 10 times the weight of an apple, such as your textbook, are things on the order of tens of newtons. Figure out what your weight would be in newtons. If your mass is somewhere between 50 to 100 kilograms, then your weight would be 50 times 10 to 100 times 10 newtons, or 500 to 1,000 newtons. So hundreds of newtons are the weights of children to adults. A gram is about a third of a penny. A third of a penny weighs at the surface of the earth. What does a third of a penny weigh at the surface of the earth? 1 penny weighs 3 grams. A gram is a very light measure of mass. A cube of water 10 centimeters on a side was the old standard for measuring a kilogram. That was the old standard of a kilogram. Now, platinum iridium cylinder is our new standard. Recall Galileo's experiment, where he rolled objects and released objects as slide down ramps, increased the angle of the ramps to measure the accelerations, the time, the distance, and the velocities, and found all objects go down ramps to gain the same speed over the same time frame. The legend has it he dropped objects from the Leaning Tower of Pisa and showed that the objects all fall at the same rate, regardless of what the object is, as long as air resistance didn't come into play. So all objects free fall identically if we can ignore air resistance, and for things like paper and leaves we cannot, but heavy objects that don't catch much air we can for short distances, for quick falls. So if the acceleration were equal to the weight, then a boulder would have a greater acceleration than a pebble. But Galileo has demonstrated this is not true. Whether the object is going down a ramp, a steep ramp, or falling from a vertical ramp, just free falling from a building. Pebbles and boulders do not fall at different rates. It makes sense to think that the greater weight, the greater force for the object that has a greater weight would result in a greater acceleration. Greater force, greater cause, greater effect, greater acceleration. But that's not the case. Acceleration is not the same as force. Greater force does not mean greater acceleration necessarily, because there's the inertia, the mass that comes into play. The boulder has a greater weight, a greater force on it from the earth, but the earth pulling on the boulder is pulling an object with more inertia. Newton's explanation: the greater the mass, the greater the force needed to accelerate it, and it's directly proportional. For instance, if a brick is dropped, there's a force of the earth, the weight of the brick. The force per the mass is the acceleration. If it's in free fall, the acceleration is 9.8 meters per second squared, or about 10 meters per second squared. So force per mass is equal to g on objects in free fall. If an object is twice as heavy, it's as if it's made up of 2 bricks or 2 masses. Each brick of the same weight has the same force, or twice the force, per twice the mass, resulting in the same acceleration of g. Whether the 2 masses are side by side, attached or not attached, they all fall the same way. If you attach a heavy object to a light object, or have a heavy object and a light object nearby, they would have to fall the same exact way. The earth, the pull of the earth, the force on the earth, the weight of the heavy object scales with the mass to give the same acceleration. Or, if an object that was twice as heavy fell at a different rate, then we consider that as twice as heavy to be made up of 2 parts, such as the 2 bricks. And if the bricks themselves would fall at the same rate, then putting 2 bricks nearby or tying 2 bricks together shouldn't make a difference in terms of how they fall. So an object that's twice as heavy, the same thing as an object, 2 objects of half the mass falling the same way as an object that's twice as heavy. It couldn't make sense otherwise. This was Newton's argument, and it's shown to be true with experiment. A pebble versus a boulder. If a pebble is dropped and a boulder is dropped, they fall the same way. Acceleration relates to the force, the weight, divided by the mass. For a boulder, the acceleration is the same because let's say the boulder is 100 times the weight of a pebble. We can think about it as made up of 100 pebbles. So it has 100 times the mass and it has 100 times the weight. The force of the Earth scales with the mass. 100 times the weight divided by 100 times the mass gives you the same acceleration. The boulder falls the same way as 100 pebbles, all nearby, are all stuck together. What is apparent weight? It's the weight we appear to have by measures of things pressing up on our feet, or on our butts, or things that press up and fighting against gravity. For instance, if you're in an elevator, you feel heavier when the elevator is accelerating upward. Or you can feel lighter when the elevator is accelerating, depending on the direction of your motion and the acceleration. If you're speeding up or slowing down, you can feel heavier or lighter in the elevator. Let's examine that. From your textbook, a person here is standing on a spring scale, an ordinary scale. Ordinary scales, such as a foot scale that you stand on, work by compressing a spring when you stand on it. How much the spring is compressed is calibrated to record your weight. So this person is looking down on his foot scale and a spring scale. He stands on the spring scale, and the spring scale we see, the force of the spring in the force diagram is greater than his weight from gravity. So the spring scale force upward is greater than the weight from gravity downward. The spring scale would read of an apparent weight greater than his actual weight from gravity. So he feels heavier because the spring pushes up on his feet more so than the earth pulls him down. If he is at rest, the spring pushes up the same as the weight of gravity pulling down. His apparent weight from the scale is the same as his gravitational weight when he's at rest. But when he's accelerating in the elevator upward, the spring is pushing him up more so than the weight of gravity to accelerate him, to lift him up at a greater speed. To accelerate him up, you have to have the spring scale, the thing he's in contact with, lift him up more so than the weight of gravity pulling him down. Otherwise, he won't accelerate on this way up. So his apparent weight is from his contact force. In this case, his one and only contact force on his feet. His feet, his legs, his body feels heavier than normally at rest because it's being pushed by the scale, or if he was standing on the elevator floor, being pushed by whatever he's in contact with more so than the earth pulls him down. So his apparent weight, he feels heavier. His apparent weight is greater than his weight, resulting in a net force and an acceleration upward. So net force and acceleration, by Newton's second law, a net force is the cause of acceleration. Net force points always in the same direction of acceleration. Net force relates to acceleration by mass, and mass or inertia can't change direction, so net force and acceleration are always parallel. If this person is going up in the elevator, then his velocity and acceleration are parallel, and you already know that if acceleration vectors and velocity vectors are parallel, this is a gain in speed. How does this person gain speed? There must be more force up than down in the direction of his motion, upward, so that he can gain speed. You have to have a net push in the direction of motion to gain speed. The greater push from the spring scale versus the pull downwards from the force of the earth, from his weight, from gravity, is accelerating him upward, pushing more so in his direction of motion up. The same force diagram, but let's say we're told the person is going down. We can't tell from a force diagram motion. We can tell from a force diagram whether there's acceleration, which implies a change of motion. But let's say now the elevator is on its way down with the same force diagram. The spring scale pushes up on him more than the earth pulls down. His gravitational weight is less than his apparent weight. He feels still heavy in this elevator on the way down. There's an acceleration or net force up as he's going down. You know that if acceleration and velocity are antiparallel, it means something is slowing. In this case, he's going downwards, following the velocity vector, so he's slowing downwards. How do you slow an object? You push against its motion. If you have multiple forces, you have to have a net push a greater push against its motion to slow it down. The object is going down, so there has to be a greater push or pull, in this case from the spring, a greater push from the spring upwards on the man to slow him on his way down. So his apparent weight is still greater than his gravitational weight, but in this case, from exactly the same force diagram, but being told the motion is downward, he feels heavier because he's slowing on his way down. As you're in an elevator, your apparent weight could equal your actual weight in the first diagram for the girl, when your apparent weight is your normal weight or gravitational weight when you're at rest or when you're moving at a steady speed. Our first law example, when you're in uniform motion, when the net force is 0. If the net force is not 0, then the force of the scale, the force of the elevator on you, whatever you're in contact with, is different than the weight of gravity. They're unbalanced. The vectors do not add up to cancel out. You have a net force, you have an acceleration. If your acceleration or your net force are with your velocity, then you're gaining speed. If your net force and therefore your acceleration are opposite or anti-parallel to velocity, then you're slowing. Anytime you have a net force, you have an acceleration. And if you have acceleration, therefore you're gaining or losing speed. And with a net force, it means your apparent weight is not the same as your gravitational weight. So if you have an apparent weight different from your gravitational weight, it's because you're slowing or gaining speed. So you can have greater than your normal weight when you're gaining speed or slowing, as we just saw. And you can have your apparent weight less than your gravitational weight. Also can be from when you're gaining speed or slowing, but in the opposite directions that we just discussed. The extreme would be if the cable was cut, the elevator was let loose, so there's no brake systems at all, then you, the scale, and the elevator would all fall in free fall. There would be only one force, the force of the earth, your weight pulling on all these objects, your weight pulling down, the weight of the scale pulling down, the weight of the elevator pulling down. All objects would be accelerating at g, falling down. There would be nothing pushing up on you. Nothing pushing up means no apparent weight. You would feel weightless. Not because there's no gravity, you still have a gravitational weight pulling you down, but nothing pulling up makes you feel weightless. So taking it from that extreme, anything pushing up on you gives you apparent weight. If you push up, the push-ups on you equal your gravitational weight, then your apparent weight is the same as your gravitational weight, or your normal weight. If your push-up is more, then your apparent weight is heavier. If your push-up is less than your gravitational weight, you feel lighter. Those are the results when you have acceleration in balanced forces. Considering all this, choose the best force diagram that matches the situation described for an elevator suspended by a cable moving upward and slowing to a stop. On Blackboard, submit your answer to the second question. If the elevator has descended from the 50th floor and it's coming to a halt at the first floor, as it does, is your apparent weight in this situation, as you're going down from 50 to the 50th floor to the first floor, but slowing on the way down, is your apparent weight less than, equal to, more than your true weight, your gravitational weight, or is it 0? And on Blackboard, submit your answer with your explanation of how you got your answer to this problem. A 50-kilogram student gets in a 1,000-kilogram elevator at rest. As the elevator begins to move, she has an apparent weight of 600 newtons. She's 50 kilograms, so our apparent weight of 600 newtons means her apparent weight is greater than our 50 kilogram times g, her 500 newton weight. This lasts for the first 3 seconds. How far has the elevator moved and in which direction at the end of 3 seconds? To do this, you need to consider that her apparent weight is greater than her weight from gravity, 600 newtons, versus her mass of 50 kilograms times g to get her weight to be about 500 newtons. So if her apparent weight is greater than her gravitational weight of 500 newtons, then she's accelerating. It's a second law example. There's a net force. It acts for 3 seconds, so I have an acceleration for 3 seconds. So the net force and acceleration must be pointing up. She's going from rest. This acceleration then changes the initial velocity of 0 to something. The apparent weight of 600 newtons greater than the gravitational weight means there's more force upwards, apparent weight of 600 newtons, versus the pull 500 newtons downwards. So there's more force up. So the net force is up. So the acceleration is up. With initial velocity of 0 and acceleration up, the final velocity or later velocities must also be going upward. This is why she's going upward, because she's being accelerating upward by more push or pull from the cable or more push from the floor upward. The net force divided by her mass is her acceleration. Not any old force, but the net force divided by mass is her acceleration. Once we have our acceleration, we then can use our familiar kinematic equation. The displacement vertically, 1/2 that acceleration, force per mass, times the time we're given, square that, to find out what our displacement was vertically. Submit your answer to this question on Blackboard. These 5 scenarios are 5 separate independent force diagrams. Those vectors are force vectors on an object. Create your own stories or scenarios what this can possibly represent. But in general, which of these objects are moving? Is the force diagram in A, B, C, D, or E, or a combination of those depicting motion? Is it all of them, none of them, or can you not tell? Or is it only the balanced force diagrams of A, B, and D? Or only the unbalanced force diagrams of C and E depict motion? The unbalanced diagrams are examples of Newton's second law, C and E. The balanced force diagrams, A, B, and D, are examples of Newton's first law. Remember, Newton's second law tells you how an object changes its motion, by a net force. Newton's first law tells you if there is no net force, as in A, B, and D, if the forces cancel or balance, there's no change in motion. Careful what Newton's laws say, they are subtle. There's the second law about a change in motion, the first law about no change in motion. Italicized is the key word, change.